Design a system to manage a chain of 5,000 hotels with 1 million total rooms, while maintaining a strict 10% overbooking allowance. That is the baseline engineering constraint for a global hospitality booking engine. This three-tiered funnel chart breaks down the actual traffic distribution. Users browsing detail pages generate about 300 queries per second. Only a fraction of those users proceed to checkout, dropping the load to 30 queries per second. By the time users actually click the final confirmation button, the true write volume shrinks to an average of just 3 transactions per second. That final execution layer, processing a mere 3 transactions per second, is the critical bottleneck. A write volume this low means system failures in this domain are rarely caused by hardware throughput limitations. Instead, they are caused by concurrency collisions and data anomalies. Success here depends on solving for correctness and concurrency long before raw throughput ever becomes a concern. The required RESTful endpoints map the booking funnel. GET requests handle the high-volume queries for hotel details and room availability. The state-changing action occurs at the POST endpoint for reservations. The client payload here must carry the exact date range and the target hotel ID. This entity relationship diagram maps a naive schema approach, where a specific physical room ID is linked directly to a user ID the moment a reservation is made. That model works for platforms like Airbnb, where users book specific properties. It fails for traditional hotels. Physical room numbers are assigned dynamically by front desk staff at the exact moment of check-in, not weeks in advance online. The system must therefore reserve a specific room type over a continuous date range, rather than a discrete physical space. This updated entity relationship diagram introduces the room type inventory table, tracking physical inventory against the reserved count. The composite primary key locks 3 variables together: hotel ID, room type ID, and a specific date. This granularity allows the database to increment or decrement aggregate daily inventory levels without ever locking individual room entities. If the data model is misaligned with the physical reality of the business, it breaks system logic before a single network request is ever processed. Consider a user reaching the final checkout screen. Their application generates the unique reservation ID required for the idempotency check. The impatient user double-clicks the Complete Booking button, sending 2 identical post requests. The first request reaches the database, mapping the client's idempotency key to the primary key. Milliseconds later, the second request hits the unique constraint on that exact key and is dropped. The API safely returns the success status of the first execution to the client, keeping the duplicate attempt completely invisible to the user. Leveraging native database constraints guarantees exactly once processing far more reliably than relying on fragile client-side UI blocks. The most dangerous concurrency threat is the last room available race condition. 2 independent users attempt to claim the exact same inventory simultaneously. User 1 and User 2 simultaneously query the database, both reading 99 reserved rooms. Both threads verify the math and proceed. Both increment the count to 100. The result is 101 users holding bookings for only 100 physical rooms.
One potential solution is pessimistic locking, achieved by passing a select for update statement. Serializing updates this way creates massive lock contention. Under heavy traffic, transaction wait times compound, and database performance degrades rapidly. Another option is optimistic locking. This requires adding a version tracking column to the row and rejecting any update if the version number shifts mid-transaction. While it protects the data, it destroys the user experience. Competing users receive constant failure notices and are forced to continually retry their bookings manually. This SQL code block displays the actual solution: native database constraints. This constraint forces the database engine itself to evaluate the subtraction at the exact moment of commit. If any transaction pushes the result below 0, the engine rolls it back instantly. To satisfy the business requirement of a 10% overbooking allowance, we simply multiply the total inventory by 1.10 within this exact same SQL constraint. True concurrency defense pushes validation logic down into the ACID database layer, actively avoiding application layer bloat and race conditions entirely. Processing 3 writes per second is trivial, but satisfying the 300 queries per second of read volume without crushing the core inventory database requires an additional layer. we introduce a Redis cache layer. It sits directly in front of the database to absorb the massive volume of availability queries. The Redis structure requires a highly specific key, the hotel ID, _ room type ID, _ and the date. Live write traffic updates the core relational database first. Those changes then propagate to Redis asynchronously via a change data capture mechanism. Because this update is asynchronous, replica lag creates a vulnerability. The cache can become temporarily stale. In this edge case, the cache falsely reports an empty room is available, and a user clicks to book it. The system does not break. The write request bypasses the cache and hits the database. The mathematical constraint evaluates the real inventory, catches the discrepancy, and rejects the write. Accepting eventual consistency at the edge allows for massive horizontal scale without sacrificing absolute correctness at the core. If the architecture is applied to a global aggregator like Expedia or Booking.com, traffic scales exponentially. When a single relational database reaches its physical input-output limits, database sharding becomes mandatory. Incoming traffic is routed across multiple servers using a specific sharding key logic, a hash of the hotel ID modulo the total number of servers. Upstream data modeling choices, specifically anchoring all early queries on the hotel ID, define the absolute ceiling of a system's horizontal scalability. Modern engineering carries a strong bias toward decoupling. The instinct is to separate this architecture into isolated reservation and inventory microservices, assigning each its own database. This creates catastrophic operational overhead. If a reservation is placed but the separate payment service fails, the system must execute a cross-network rollback just to free up the stranded room inventory. Fixing data inconsistencies across independent databases requires two-phase commit protocols or complex Saga patterns, introducing severe latency penalties. The pragmatic counter-strategy is architectural restraint. We intentionally group the reservation and inventory tables within the exact same relational database boundary. This allows the system to utilize local native ASICD transactions to verify inventory and commit the reservation simultaneously, entirely bypassing the need for distributed state management. Exceptional system design requires knowing the tools available and knowing exactly when to abandon them in favor of mathematical, centralized guarantees.